Elementary Probability Theory Lecture Topics Summary. Introduction to Probability. Basic concepts of probability and its importance. Interpretations of probability. Classical, empirical, and subjective approaches to understanding probability. Addition rules of probability. Calculating the probability of one or both events occurring. Multiplication rules of probability. Finding the probability of multiple events happening together, with a focus on independent and dependent events. Fundamental rules of counting. Key counting methods, including the multiplication and addition principles. Permutations and combinations. Methods for counting arrangements and selections. People frequently use the term probability in daily life. For instance, a doctor might say a patient has a 50-50 chance of surviving surgery, while another might express 95% certainty that a patient has a specific disease. Probability measures the chance of an event occurring. It is expressed as a numerical value representing the likelihood of the event and is calculated as the ratio of favorable outcomes to the total number of possible outcomes. An outcome is a possible result of a probability event, while the sample space is the list of all possible outcomes for that event. An outcome is considered random if each possible result is equally likely to occur. A simple event refers to a specific outcome or type of outcome, and an event is a collection of one or more simple events within the sample space. Probability theory is essential for logical inference and managing uncertainty, quantifying the likelihood of outcomes on a scale from 0 to 1. It enables informed decision-making by applying various methods to measure and calculate probabilities, providing a framework for understanding and addressing uncertainty in different scenarios. In probability, if an event is represented by A, its probability is denoted as P of A. Events are independent if the occurrence of one does not affect the other. Otherwise, they are dependent. Outcomes are equally likely if each has the same probability of occurring. Various counting rules are used to determine the total number of possible outcomes in different scenarios. Complementary events are pairs of events where if one occurs, the other cannot. If event A happens, its complement is denoted as a complement, and the sum of their probabilities is always 1. For example, if the probability of rain today, event A, is 0.3, the probability of no rain, event A complement, is 0.7. The probability of any event A, denoted P of A, is such that the sum of the probabilities of all possible outcomes must equal 1. Additionally, two events are considered mutually exclusive if they cannot occur simultaneously. Classical probability assumes that all outcomes in a sample space are equally likely and is calculated by dividing the number of favorable outcomes by the total number of possible outcomes. For instance, when rolling a fair 6-sided die, the probability of rolling a 3 is 1 divided by 6, assuming each face has an equal chance of appearing. Empirical probability involves determining the likelihood of an event based on observed data rather than theoretical assumptions of equally likely outcomes. For example, if a coin is flipped 100 times and lands on heads 55 times, the empirical probability of landing on heads is calculated as 55 divided by 100 or 0.55. To determine the probability of flipping a tail on a coin, note that there are two possible outcomes, heads or tails. Since each outcome is equally likely, the probability of flipping a tail is 1 out of 2, or 0.5, which is equivalent to 50%. When rolling a standard 6-sided die, the probability of rolling a 4 is 1 out of 6, as there is only one favorable outcome, rolling a 4, out of a total of 6 possible outcomes. For example, when rolling a die, the probability of rolling an even number is calculated as the number of favorable outcomes, rolling a 2, 4, or 6, divided by the total number of possible outcomes, 6. Therefore, the probability is 3 out of 6, which simplifies to 0.5 or 50%. To determine the probability of spinning green on a spinner with 4 equally likely outcomes, divide the number of favorable outcomes by the total number of outcomes. Since there is one green section out of 4 possible sections, the probability is 1 divided by 4, which equals 0.25 or 25%. To calculate the probability of each independent event, determine the likelihood of each outcome occurring. For event 1, find P of black, the probability of drawing a black item. For event 2, find P of 1, the probability of drawing the number 1. For event 3, find P of odd, the probability of drawing an odd number. Lastly, for event 4, find P of F prime, the probability of drawing a prime number. To calculate the probability of each independent event, use the following values. The probability of drawing a black item is 4 divided by 8, the probability of rolling a 1 is 1 divided by 8, the probability of getting an odd number is 1 divided by 2, and the probability of selecting a prime number is also 1 divided by 2. In a sample of 50 people, the frequency distribution for blood types is as follows: 21 people with type O, 22 with type A, 5 with type B, and 2 with type AB. To find the probabilities, the probability that a person has type O blood is 21 divided by 50, b. The probability that a person has either type A or type B blood is 27 divided by 50, c. The probability that a person has neither type A nor type O blood is 7 divided by 50, d. The probability that a person does not have type AB blood is 48 divided by 50. Two events are mutually exclusive if they cannot occur simultaneously, meaning they have no outcomes in common. For example, in the context of rolling a die, getting an odd number and an even number are mutually exclusive events because a single roll cannot result in both. In contrast, getting an odd number and a 3, or getting an odd number and a number less than 4, are not mutually exclusive since the outcomes overlap. Similarly, getting a number higher than 4 and a number less than 4 are mutually exclusive because one roll cannot meet both conditions at once. When two events, A and B, are mutually exclusive, they cannot occur simultaneously, there is no overlap between them. A box contains 3 glazed donuts, 4 jelly donuts, and 5 chocolate donuts, making a total of 12 donuts. To find the probability of selecting either a glazed or a chocolate donut, note that these events are mutually exclusive. The probability of selecting a glazed donut is 3 divided by 12, and the probability of selecting a chocolate donut is 5 divided by 12. Adding these probabilities, we get 2 out of 3. When events A and B are non-mutually exclusive, it means they can occur at the same time and have some overlap in their outcomes. In a hospital unit with 8 nurses and 5 physicians, where 7 nurses and 3 physicians are female, we want to find the probability that a randomly selected staff member is either a nurse or male. The calculation is as follows: the probability of being a nurse is 8 divided by 13, the probability of being male is 3 divided by 13, and the probability of being a male nurse is 1 divided by 13. Using the formula for the union of two events, P of nurse or male equals P of nurse plus P of male minus P of male nurse, we get 10 divided by 13. Two events are independent if the occurrence of one does not impact the occurrence of the other. For two independent events, A and B, the probability of both events occurring together is the product of their individual probabilities. To find the probability of flipping a head on a coin and rolling a 4 on a die, multiply the individual probabilities. Thus, the combined probability is 1 out of 12. The sample space for the coin includes heads and tails, while the sample space for the die includes numbers 1 through 6. Dependent events. Dependent events are those where the outcome of the first event influences the probability of the second event. For instance, having high grades can increase the likelihood of receiving an academic scholarship, as the first event, high grades, affects the outcome, scholarship eligibility. A person has a collection of 30 CDs, including 5 country music CDs. To find the probability that two randomly selected CDs are both country music, calculate it as follows: since the events are dependent, the probability is P of C1 and C2 equals 2 out of 87. Conditional probability measures the likelihood of event B occurring given that event A has already occurred. It is calculated by dividing the probability of both events A and B happening together by the probability of event A. This is derived from the multiplication rule for dependent events. In a recent survey of 100 people about permitting women in the armed forces to participate in combat, probabilities are calculated based on survey results. For part A, find the probability that a respondent answered yes, given that the respondent was female. For part B, determine the probability that a respondent was male, given that the respondent answered no. To find P, Y divides F, the probability that a respondent answered yes given that they are female, use the formula P, Y divides F, equals P, F intersection Y, P of F, P, Y, F. Here, P, F intersection Y, is the probability that a respondent is both female and answered yes, which is 8 out of 100, and P of F is the probability of selecting a female, which is 50 out of 100. Thus, P, Y divides F equals P, Y, F. P, Y divides F is calculated by dividing the probability of females answering yes by the probability of selecting a female. Fundamental counting rule states that if there are m ways to perform one action and n ways to perform a second action, then the total number of ways to perform both actions in sequence is m times n. For instance, if you have 3 options for one event and 4 options for another, the total number of possible outcomes is 12. When a coin is tossed and a die is rolled, there are 2 possible outcomes for the coin, heads or tails, and 6 possible outcomes for the die, numbers 1 through 6. Therefore, the total number of possible outcomes for this sequence of events is 12. There are 4 blood types, A, B, AB, O, each with 2 Rh factors, Rh plus and Rh minus, and donors can be either male or female. Therefore, the total number of possible blood labels is calculated by multiplying the number of blood types, Rh factors, and genders. 4 times 2 times 2 equals 16 different possibilities. For a 4-digit university ID using the digits 0, 1, 2, 3, and 4, if repetitions of digits are allowed, there are 625 possible combinations. If repetitions are not allowed, the number of combinations is 5 times 4 times 3 times 2 equals 120. A factorial, denoted by n factorial, is the product of all positive integers from 1 to n, defined as n factorial equals n times n minus 1, times n minus 2, times 1 for n greater than 0, with 0 defined as 1 by convention. Factorials are essential for computing permutations and combinations, as well as other mathematical applications. For example, 5 factorial equals 5 times 4 times 3 times 2 times 1 equals 120. A frequent traveler wants to rank 5 theme parks from best to worst. There are 120 possible ways to rank all 5 parks, 5 factorial. If the traveler only wants to name the top 3 parks, there are 60 possible ways to do so. 5 times 4 times 3 equals 60. A permutation is the arrangement of n objects in a specific sequence, where the order of the objects matters. To determine the number of different ways to choose a classroom president and vice president from 7 students, we use permutations since the order of selection matters. The calculation is given as 42 possible outcomes. To determine the number of possible ways to cast 3 specific female roles, lead, sub-lead, and villain, from 8 applicants, we use permutations since the order of selection matters. The number of permutations is calculated as 336 ways. A combination refers to the selection of distinct objects where the order does not matter. It is used in scenarios where the arrangement of the items is irrelevant, focusing solely on the choice of items themselves. The CEO of a large company has 12 vintage cars and wants to select 5 for an exhibition. To determine the number of different ways to choose 5 cars from the 12, we use the combination formula, which is calculated as 792. Therefore, there are 792 different ways to select 5 cars from the 12. In an arts club with 7 women and 5 men, a selection committee of 3 women and 2 men is to be formed. The number of possible committees can be calculated using combinations as 350 possible combinations. Thank you for watching.